So what if we have lone pairs involved? We've talked about different shapes where all of the bonding groups were bonds. No, where all of the electron groups were bond. Of course bonding groups are bonds. So we can have two different kinds of geometries. We can have an electron geometry. That's the arrangement of the electron groups. And then when we have lone pairs, especially, we talk about a molecular geometry. That's the arrangement of the atoms. If there are no lone pairs, then the molecular geometry is the same as the electron geometry. So let's look at ammonia. Let me draw the Lewis structure for you. I think I inhaled some chalk dust or something. I know. I guess it's got calcium in it, but... Okay, so here's the Lewis structure for ammonia. When we look at the central atom, we see that it has 1, 2, 3, 4 groups. 4 groups will arrange themselves in a tetrahedron. So we'll get a shape like this. 3 of these groups are bonds to hydrogen. The 4th group is the lone pair. So the electron geometry, the geometry of the electron groups, is a tetrahedron. But when we talk about the molecular shape, that lone pair is just 2 electrons, right? And they're busy doing their standing wave orbital wave function thing, but they're too small to see. And so I think of these as invisible. So you imagine what the balloons would do. What would 4 balloons do? And then you make one of those balloons invisible. You don't pop it, you just make it invisible. So I'm going to make this invisible because I can. He's going to be invisible. Okay, so if he's invisible, that doesn't affect the spacing of these guys at all, because he's still there, we just can't see him. But this is the shape. Now that's not a tetrahedron. This is called Trigonal Pyramid. We had trigonal planar before, but that was flat like a pancake. This is sticking up a little bit. It's a pyramid. It's a real shallow pyramid, but it is a pyramid. So this is Trigonal Pyramid. Any questions?
It's like that because you have those 2 electrons up there.
Yeah, we got the 2 electrons up here, and they are repulsive to these, the electron groups in these bonds. And so they make a tetrahedron, but it's like one end of it is invisible when we think about the molecular geometry. The other thing about lone pairs is they are more repulsive than bonding pairs. You know, so maybe you've got this, there's 4 people, you know, and you're all trying to get away from each other because you really, really hate each other. But then this one person is more awful than the rest. And so you're willing to be a little closer to these other people you hate because that person's worse. That's the lone pair. Okay, very repulsive. They spread out more in space. Here we have an illustration of a bonding electron pair. So the space occupied by that bonding electron pair is confined between the 2 nuclei. But the lone pair can spread out more, and so it takes up more space. So you can think of it as taking up more space, or you can think of it as being more repulsive. So with 4 electron groups, the ideal geometry would have equal angles of 109.5, right? Because the lone pair is more repulsive or takes up more space, it's going to push the others a little closer together. So the angle here, instead of 109.5, is 107. Not a huge change, but sometimes that's significant. Any questions? You don't have to memorize this angle, 107 for ammonia. You should know that the angle for an ideal tetrahedron is 109.5. That's an important number to know. For this, what I want you to be able to say is, because of the lone pair, the angle between the hydrogens is going to be less than 109.5. Okay, let's look at water. Draw the Lewis structure for water. I'm just going to do these Lewis structures quickly because we've gone over this before. So there's the Lewis structure for water. We look at the central atom. How many electron groups? 4. Lone pairs are groups. Single bonds are groups. So there's a total of 4. 4 electron groups makes a tetrahedron. So here's our tetrahedron. We have 2 single bonds and we have 2 lone pairs. The electron geometry is tetrahedral. The molecular geometry is just the atoms. So pretend that these guys are invisible. When we can't see those anymore, what shape is left? It's this. And that has the very fancy name, bent. Right? So we've got some of the like trigonal pyramidal, right? You know, big fancy words, and then we've got bent. We got a couple other simple ones coming up too. So the molecular geometry is bent. You've got 2 bonding groups and 2 lone pairs, total of 4. You're going to get a bent molecular geometry. And again, those lone pairs are going to affect the angle. If this was ideal, we'd have an angle between those hydrogens of 109.5. But the lone pairs are more repulsive. And now there's 2 of them. So that's going to squeeze these hydrogens together even a little more than it did in ammonia. And this angle is going to be 104.5. Again, I want you to be able to predict that it's less than 109.5. Any questions? So here's a relative repulsion of electron groups. Lone pair is the most repulsion. A lone pair with a bonding pair is in the middle, and 2 bonding pairs with each other are less repulsive than the others.
What about a single electron?
I think a single electron with any of those, like a single electron with a bonding pair, would be less repulsive than bonding and bonding. That's probably not going to come up, though. So we see this effect when we look at bond angles for these 3 simple molecules. Methane, having no lone pairs, has ideal bond angles for a tetrahedron. Ammonia, it's smaller, it's 107, because there's 1 lone pair, and with 2 lone pairs, it gets even smaller, 104.5. Any questions? So let's draw the Lewis structure for sulfur tetrafluoride. Well, let's start out by putting sulfur in the middle and attaching the fluorines around it. Most of the time, not always, but most of the time, if you have something like this where you've got one of one element and several of the other, this one is going to be in the middle. A lot of the molecules are symmetrical. Not all of them, but most of them are symmetrical. Then we have to consider how many valence electrons do we have for the whole molecule. Sulfur has how many valence electrons? 6. There's 4 fluorines, and they each have how many? 7. So we got 4 times 7 is 28, and 6 is 34. Did I do that right? That sort of math, you know, is great if you can do it in your head, but it's more important to get it right. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We have 2 more electrons. Where are we going to put them? On the sulfur. When we do that, and we can do that because sulfur is in period 3. Period 3 elements can expand their octets. Fluorine can't. Fluorine cannot take more than an octet of electrons. And if you go through and calculate the formal charges for all of these, they're all going to end up being 0. And so we know that's a good thing. So now looking at this, we count number of electron groups. We have 1, 2, 3, 4 from the bonds, and another one from the lone pair, 5 groups. 5 groups make that bipyramidal or trigonal bipyramid shape. Okay? But one of them is a lone pair. The trigonal bipyramid does not have equal bond angles. right? The angle between an axial and an equatorial is 90 degrees, but the angles between the equatorial is 120. So when we have one lone pair with something like this, the trigonal bipyramid, the positions are not all the same, and so we need to put it in where it's got more space. It has more space in the equatorial part. So it's going to be part of the 2-2. It's going to be around the equator, with this being the North Pole and the South Pole. Does that make sense? This is one of those things that you need to be able to visualize. So if we put it around like this, and then we make that invisible, this is the shape we end up with. And that's called a seesaw. Makes you want to go to the park, doesn't it? So the seesaw, it doesn't really look like a seesaw when you draw it that way. But if you think of it, so here's one seat, and here's the other seat, and here's, what do they call that? The fulcrum? The part in the middle? And so then it's got legs that it stands on. So this one's behind and this one's in front. So it's got these two little legs that it's standing on, and then you've got the two seats. And so you can see how that could be a seesaw.
No, will that happen?
What about bromine trifluoride? So here's the Lewis structure. 1, 2, 3, 4, 5 groups. 5 electron groups, trigonal bipyramid. 2 lone pairs. So the electron geometry is trigonal bipyramid, and then we put the lone pairs in, again, putting them in places where they have more room. The angle here is 120 degrees instead of 90 degrees. And the repulsion between these two guys is the greatest, so we want to put those equatorial. And then when we make those invisible and look at what we have left, we have a T shape. There's another really fancy, ooh, that's T-shaped, right? Again, if you tip it on its side, it's a little easier to see. So that'd be like this guy, right? It's shaped like a T. Any questions?
So will we need to know we need to know the degrees for reference so we can answer questions, but do we need to memorize degrees for certain things?
I think the only one you really need to memorize is that a tetrahedron is 109.5. You should know that this is a 90-degree angle, and that the angle on these equatorial ones or on a trigonal planar is 120. I think that falls into, or maybe just barely into, what's expected as common knowledge. But the 109.5, I don't remember a part of math where we talked about taking a sphere and dividing it into 4 pieces and how you would come up with 109.5. I think I erased that part of my life. I don't know. But a 360-degree circle divided into 3 pieces, okay, that's 120 each. Or divided into 4, and that's 90. I think we should remember that. Let's look at this one, Xenon Difluoride. So we look at the Lewis structure, again, 5 groups, 1, 2, 3, 4, 5. Trigonal bipyramid is the electron geometry. But now we have 3 lone pairs. Again, we're going to put those lone pairs around the equator, around the 2-2 skirt, where they have more space. And then what we have left is a linear molecule. You wouldn't necessarily expect that with all these electron groups. It's a linear molecule. I think of this as the little girl wearing her leotard and her tutu's invisible. She's not naked. That would be gross. Okay, so this one's linear. Any questions? 6 electron groups with lone pairs. Bromine pentafluoride. Here's the Lewis structure. 6 electron groups, 5 bonds, 1 lone pair. So 6 groups is the octahedron, like these balloons. So you make the octahedron. That's the electron geometry. We have one lone pair. It's invisible. What do we have left? Well, this is called a square pyramid. I tried to draw this yesterday. I didn't do very well. Let's see if I can do better today. Not much. You kind of get the idea? It's a square at the bottom. So you can have a triangular pyramid, a pyramid with a triangular base, or you can have a square pyramid that has a square base. When we look at my balloon sculpture here, imagine that the bottom balloon, the bottom purple balloon here, is invisible. And that is the shape that we're talking about. It's a base that's a square coming up to a point. What would these bond angles be? 90. Maybe squished a little bit because of the lone pair repulsion, but it's not a big deal. Does the lone pair have to be down here? No. It's 90 degrees everywhere. They're equivalent. The trigonal pyramid is the only one where you have two different kinds of positions. The others, they're all equivalent. What if you have two lone pairs? Xenon Tetrafluoride. So here we've got 4 single bonds and 2 lone pairs. So here's our octahedral electron geometry. If we put 1 lone pair on the bottom, now we have to choose where to put the second lone pair. The repulsion between the lone pairs is greater than the repulsion between a lone pair and a bonding pair. So this lone pair has to be on the opposite side. Because if we put the second lone pair in any of these positions, the angle between the lone pairs would be 90 degrees. And it's definitely going to prefer this, where the lone pair angle is 180. And then it's got 90 degree-ish angles with the bonding pairs. So that's called square planar. So that's this balloon structure again, where both of the purple balloons are invisible. They're lone pairs. And so what you have left is a square planar. Questions? These bond angles are going to be 90 degrees. These guys are repulsive, but they're repelling from opposite sides, and so their effects cancel out, and the bond angles here aren't going to be affected at all. There's a chart showing all the stuff we just talked about. Yesterday in lecture, as soon as I popped that up, somebody said, "Do we have to memorize that?" I was like, I'm glad you asked. No, you don't have to memorize it. You could memorize it, but I think it's much easier to visualize balloons, okay? So all of this information here, if you think about the balloons and understand the process here, you don't really have to memorize it, you just think about it. You need to remember the names of these, some of these shapes have kind of funky names. I suppose you could say you have to memorize that, but that's not very much. You look at the number of electron groups on the central atom. You imagine, okay, how would that many balloons get away from each other, right? Get yourself some balloons and string and do it at home if you want to, so you can see how it works. So you get your electron geometry by arranging the electron groups just like balloons would arrange themselves. And then you look at the lone pairs and you make those balloons invisible, and then the molecular geometry is the part that you can see. It's the atoms.
So it's molecular geometry. That
We're generally getting at the molecular shape. That's usually what we want. There might be questions, though, to ask you what the electron geometry is. And you have to look at the electron geometry first when there's lone pairs, because they're not going to be the same. So summarizing VSEPR theory. Geometry of the molecule is determined by the number of electron groups on the central atom. Again, the electron groups on the terminal atoms don't matter at all. We're just looking at the central atom. We figure out the number of electron groups from the Lewis structure. You have to be able to draw a Lewis structure. What counts as an electron group? A lone pair, a single bond, a double bond, a triple bond, or a single electron. The single electrons will only be found in free radicals. You can't take a lone pair and say it's two single electrons, so don't do that. The geometry is determined by the repulsions. They spread out to minimize the repulsions. The bond angles can vary a little bit. Multiple bonds are bulkier than single bonds, and lone pairs are more repulsive than bonding pairs. So that's the summary.